In this sublesson, we're going to start working with Cassandra by defining some schemas for us to store some data. The schema in Cassandra is just like a schema in a relational database. It describes the database structure so you know how you can store data. Now, as I mentioned before, Cassandra is a column-oriented database, so the way it stores data is pretty different compared to a standard SQL database. I found one of the easiest ways to think about it is not like in terms of like a relational database with like tables and rows and things like that. I mean, there are some concepts that are the same. So first, Cassandra has what's called a key space. Now that is kind of roughly equivalent to a database in a relational database. So the first thing you're going to want to do is to create a key space in Cassandra. Now we can do this using either the Cassandra CLI tool, or we can do it using the Cassandra CQL client. Now, the CLI tool is the older interface to Cassandra. It's the Thrift-based interface. Thrift is a programming interface that they had used for building the functionality. CQL is kind of the evolution of Cassandra's API. So the goal there is that it defines a kind of structured language like SQL so that you can send commands to the server and get them executed server side. And the reason they did this is because they found as they were adding functionality to the API, when they were doing it through Thrift, the library authors who were authoring client libraries for Cassandra had too many updates to keep up. So instead, they said, we'll just define a generic CQL interface so that you can send commands just as text, and they'll get processed server side. So that when they add functionality in the API, they can get at that through the clients without ever having to update the clients. So because of that, we're actually going to use the CQL interface. So let's start this up. Now, when you start CQL, you can start it up with either version 2 of CQL or version 3. We're going to be using version 3. It has support for some features that we'll be using later. All right, so the first thing we want to do is we want to create a key space. We'll call this BigData since that's what we're working with. So create key space BigData with the strategy class org.apache.cassandra.locator.simple-strategy. So what the strategy class is it helps Cassandra determine where to place replicas of data. The simple strategy is fine for us because we only have the one server. But you can also implement strategies that are rack aware or data center aware if you want to enable replication from like one data center to another, in which case you'd want to be able to specify in your key space how that replication happens. And strategy options, replication factor of 1. And what that means is every bit of data that you write into Cassandra will only be stored once. Obviously, that's what we have to do because we have a single machine cluster. But if we had a multiple machine cluster, ideally, we'd have a replication factor of probably 3. And the reason for that is twofold. One, it gives you a performance benefit on reads. So if you have copies of the data living on 3 different servers, that means a data read can go to any one of those 3 servers and get at the data. And the second reason you want to do that is because it gives you redundance and fault tolerance if one of the machines goes down. Describing how the replication factor works and how the fault tolerance works will be a little bit easier if I show you with a picture, a drawing of multiple systems writing data. And this will also give me a chance to explain how the writes and reads from the client from a Cassandra client work. So first, let's assume that we have a cluster of Cassandra machines. So say we have one here, another here, another here, another here. We have a replication factor of 3 on our key space. Now all 4 of these computers can talk to each other. So what happens when we write in some data? Well, in the case where you're writing data and you only have a consistency level of 1 set, you only write that data on one computer here before you return a response to the client. Then at a later time, the data will be written out to the other computers that replicated with that key. So another option is to specify a quorum level write. What that does is if you write data here, before returning a response to the client, it will write data to one of these other servers. And then it will return a response. So as you can see, that gives you a certain amount of high availability and redundancy, so that if one of these computers fails, you still have another one that has a copy of the data that can serve up reads. So we can also discuss how partition tolerance works. So let's take the example. We're writing a piece of data to this server, and it wants to live on the 2 servers next to it. And say this link gets cut. Now, if you have a consistency level of 1 on the right, you'll just return a response to the client, which is fine. And then if a connection comes and hits here, they'll get that data. Now, if they come and they hit here, they won't get that data because this partition is being cut here. If you have a consistency level of quorum defined on the read, when you hit this server, it will actually check with the other servers. So say it checks this server here, and then it checks this server here. And the 2 of them are actually in disagreement about what that data is and whether or not it exists. So what it'll then do is check with the 3rd server, which hopefully by now has gotten a copy of the data, and then it will return the result that was voted as the true result out of the 3. So the consistency level that you specify works on both reads and writes. So you can define a consistency level of 1 on a write that only goes to one computer, and that will write the data as quickly as possible, but then you can't be sure whether or not the read that you get will return that data. So generally, people use quorum level consistency on the writes, and then on the reads, they can use either quorum or just 1 if they're okay with the eventual consistency part. And quorum means that if one machine in this cluster, in this group of 3 computers fails, you're still going to be okay. All right, so let's get back to defining a schema on Cassandra. So let's create this key space, BigData. All right, now we can say use BigData. This is similar to the use command in a SQL shell that gets you into a specific database. So here's our database. Now we want to create what's called a column family. And in CQL, they actually call it, they have create table as an alias to that. Now it's a bit misleading to call it a table because it's a little bit different. So let's talk about column families and tables and the differences between them. So when you look at a table in a SQL database, it looks like an array of arrays where you have the rows defined all next to each other. And they're in contiguous space, 1, 2, down the line. Now, in a Cassandra column family, it's better to think about it as a hash of ordered hashes. So here, we have a row that's called row ID 1, and then it has a hash. And then we'd have row ID 2, and it has a hash. Within this row hash is an ordered hash, and those are the columns that exist in the row. So here we have the column name. So let's say it's a username, and whatever the value is. And let's say we have some other column, which is, we'd actually want to put it up here. So let's call it location. And that would be some value. Now, this hash is actually ordered. So these are stored in continuous spots on disk, and they're ordered by the comparator that you define. So if we're using strings as the keys for the column names, it's going to order them by the lexicographical order of the strings, although you can use other keys for the column. So some examples are you can use a timestamp UUID, you can use a long value, or you can use ASCII characters or UTF-8 characters. So let's actually go in and create a specific table. Now remember, we're going to be working with the data from the Stack Overflow posts. Say I want to create a table that stores user tags. So I want to store in this which tags a user is interacted with. And I'll define that by a user has posted a question with certain tags, or they've posted a comment or answer to a question that has certain tags. So I'll say that user has interacted with these tags. I want to store the user tags in a counted list, so I can see how many times a user has interacted with each tag. So if I've posted a question about Casandra twice and 10 answers about JavaScript, then I should expect to see those counts. So we'll want to create a table, user tags. And we're going to say there's a user ID, which is a UTF-8 string, and that's going to be the row key. That's going to be the identifier to identify that row. That's this right here. That would be the user ID. We're going to say there's a tag, which again is a UTF-8 string. And what that is going to be is the actual column name. So that's going to be this thing right here. So as I said before, if they're strings, they're lexicographically ordered. So that's how these tags are going to be ordered in this row. If I request all the columns in the row, they're going to come back in alphabetical order. And finally, we're going to say what the value is. Now, Casandra, in addition to supporting timestamps or UTF-8 strings or ASCII values or integers or longs or even raw byte values, also supports a counter type. So what that means is this is a column that has a distributed counter, so you can increment to it or decrement, and you can be sure that it works well across the cluster of machines. Finally, we have to say what the primary key is. So there we see the primary key. This first one is the row ID, and the second one is going to be the column. In CQL, this is the reason we're using the 3.0 version. This means that we're going to have a wide row. So we're going to have a row that has an infinite number of columns, or actually up to 2 billion columns. So if I get really active and post on more than 2 billion tags, we're going to have a problem, but hopefully that won't happen. Now that we've created the user tags table, let's see if we can insert some data into it and have a look at it. First, see if we can select data out of it. Of course, we don't expect anything to come back because we haven't inserted any data there. As you can see, though, the select command looks very similar to what a SQL select command would be. So here, we're going to say update user tags, set value equals value plus 1. This is how you set a counter column in CQL, where the user ID equals Paul, and the tag equals Casandra. Now, one of the interesting things to note here about Casandra is that we're calling update. Now, that's different than SQL. In an SQL database, you'd get an error if you tried to update a column or a row that didn't exist. With Casandra, it writes over whatever the value is there. So you can either do an update or an insert. Now, with these wide rows in CQL, even to do inserts, you call it like this with an update. All right, so now let's see if we can get that data. Yep, we see that the user ID Paul, the tag Casandra, and the value of 1. If we wanted to increment that again, we just do that again, and now we see the value is 2. So let's look at creating another table, another way of looking at Casandra schemas. So say we want to store all the data about posts. We want to store the ID of the post, the title, the body, the post type, the tags, the owner, and when it was created. For this, we might make something that looks a little bit more like a traditional SQL table. So the command for that is pretty simple too. Create table posts. We're going to say post ID we want, and that's going to be a UTF-8 string, and we're going to just call that the primary key right here. And we can do that because this column family isn't going to have wide rows. The rows are going to be very specifically defined. You can always add columns later, but they're not going to be like dynamic with a bunch of different column names that you don't know ahead of time. So here are the column names: the title, the body, post type, which we're just going to be an ASCII string, so it's only going to be a byte. The tags, which we're just going to keep as a comma-separated string. The owner ID. And finally, the created date. And close that out. All right. So in this lesson, we've learned a few different ways to create Casandra schemas. We've learned a few of the data types: varchars, which are UTF-8 strings; ASCII, which are normal ASCII strings; longs, ints, the counter column type, and timestamps. In the next part, we'll move on to actually writing data into Casandra from Ruby.